So far, we've thought about games in which the players need to randomize in order to find a Nash equilibrium, and we focused on penalty kicks in soccer as our leading example. Remember with the idea that in soccer, if you have a kicker and a goalie who have to decide whether to kick left or right and defend left or right, you can't be predictable, because if you're predictable, you lose. So both the kicker and the goalie need to randomize. What we did then was to think about the game with the two players, kicker and goalie, strategies now that are probabilities of randomization, having you go left or right. And we did a little bit of work on computing the payoffs to those things. What we need to do now is to actually figure out how to take this and find a Nash equilibrium. And that's our topic for this session. So let's just remember what we're up to here. The kicker in our game is going to play left or right, and he plays left with probability P. The goalie is going to play left or right, playing left with probability Q. Okay. Nash equilibrium is simply strategies P and Q, that is, these randomized strategies that are best responses to each other. Remember, it's exactly the same idea as before. Nash equilibrium is a pair of strategies that are mutual best responses. What we discovered in the penalty kicks in soccer example is there can't be a Nash equilibrium with either P or Q equal to either 0 or 1. Because that would involve one player or even both players being predictable, and that can't be a way to play in a Nash equilibrium, because if you're predictable, you get taken advantage of. So the question is, how do we figure out probabilities P and Q that actually are going to form a Nash equilibrium? Let's start figuring that out by doing this from the point of view of the kicker. Think about the kicker. If he's going to truly randomize between left and right, that is, play left with probability P that's somewhere strictly between 0 and 1, then he has to be indifferent between playing left and right. Because if he thought, for example, that left was better than right, then he'd play left all the time. But he can't play left all the time in an equilibrium, because if he does that, the goalie's going to defend left all the time, and then the kicker wouldn't want to kick left, he'd want to kick right. That means that the payoff from left has to be exactly the same as the payoff from right. So in a Nash equilibrium, for the kicker, left and right have to have equal payoffs. And the same story is true for the goalie. For the goalie, left and right have to have equal payoffs in the Nash equilibrium. So what we've got to do is figure out what those payoffs are and then find the probabilities that make them equal. Let's start this again from the kicker's point of view. Let's compute his payoff from playing left. Remember, the goalie plays left with probability Q. So if the kicker kicks left, with probability Q, the goalie has defended left, and the kicker gets a payoff of 1/2. With probability 1 minus Q, the goalie has defended right, the kicker gets a payoff of 3/4. So we've now got the kicker's payoff from kicking left. We can compute the same thing for the kicker kicking right, which payoff is going to be 1 times Q plus 1/2 times 1 minus Q. In a Nash equilibrium, those two payoffs have got to be equal. That means we've now got a simple linear equation in Q, and we can solve it for Q. And we'll see the Q that solves that is 1/3. So in a Nash equilibrium, right, Q has to be 1/3. We can do the same sort of thing for the goalie, knowing that his payoffs from left and right have to be equal. Now remember, for the goalie, he has to think about what the kicker is doing. The kicker kicks left with probability P and right with probability 1 minus P. Doing that, let's compute, for example, the goalie's payoff to left. With probability P, the kicker kicks left and the goalie gets 1/2. Probability 1 minus P, the kicker kicks right. The goalie loses, he gets a payoff of 0. Compute the same thing for the goalie defending right, and solving that equation now for P, we'll see that P has to be 2/3 in a Nash equilibrium. We've now got a mixed Nash equilibrium, right? Both players are randomizing. Notice that in this equilibrium, the kicker is kicking left with probability 2/3, and therefore right with probability 1/3, and the goalie is defending left and right both with probability 1/2. That's a Nash equilibrium. Those probabilities are best responses to each other. This Nash equilibrium has a really interesting property, and it's a common property in these mixed strategy Nash equilibria. Think about the game again from the kicker's point of view. If you just glance at this game, you would think that right is a more powerful strategy than left. And the way to see that argument is to notice that on the diagonal of the game, that is where they both do left or both do right, the kicker gets 1/2. Off the diagonal, that is where their strategies don't match, the kicker always wins if he kicks right, and he wins with probability 3/4 if he kicks left, right? Right looks better than left. Maybe this is a kicker who's just better kicking to the right. But in the Nash equilibrium, the kicker's kicking left twice as often as he's kicking right. He's using his more powerful strategy less often. That's actually a fairly common phenomena in games of this sort, and it's happening here because the kicker really is tempted to kick right a lot, but if he does that, the goalie is going to defend right all the time, and the kicker then is going to lose. Because then the strategies are going to match, and the kicker gets only a payoff of 1/2. This happens, for example, in football, where pass looks like a better strategy than run, because it gives you a greater gain when you actually use it and succeed with it, but you use pass less frequently than run typically because pass is such a powerful strategy. We'll see that that happens frequently in games of this sort with mixed strategy Nash equilibria.